All right, let's continue our discussion. Today we are going to talk about the algorithm analysis. That's basically chapter 2 of the Kleinberg and Tadeusz, which is our textbook. Today we are only going to cover 3 items out of the 4 items listed in this slide. We are going to talk about the trackability and asymptotic order of growth and some survey of common running times. So let's start with the computational trackability. So next, we want to be able to come up with a mathematical abstraction of computational trackability. So this is the trackability. So what do we mean by being trackable? A problem is trackable if we are able to design a computer algorithm or computer program that can efficiently solve the problem. But then we want to be able to come up with a mathematical abstraction to define what do we mean by efficiently solving the problem. So inevitably, we do want to be able to articulate the amount of computational resource we need to consume in order to solve the problem. Because intuitively, when you consume smaller amount of resources, for instance, you have smaller amount of running time or smaller amount of memory usage, then the algorithm is efficient and the problem that the algorithm is solving is trackable. So our next question would be, how can we articulate what sort of computational resources we need to use in a computer algorithm? So resources needed is the questions we want to ask. And here, because we do want to come up with a mathematical theory that doesn't really change too much when you change the computing devices. So this really means that our abstraction need to be able to cover all possible scenario, regardless whether this is a very ancient machine as shown in this picture, or a very modern machine, quantum machine that's really developed in recent days. We want to be able to come up with a notion of computational resource that's needed by this kind of resources. By this kind of computer. For example, when we want to use these very ancient computers, and then when we talk about the computational resource associated with running a particular program under this machine, basically, usually we really just mean that how many times do we have to turn the crank over here. The more crank you turns, the more computational resources we are consuming. Here, the resources is mainly the running time. So next, we need to describe about the computation models. Here, a computation model is really just an abstract way to describe computation procedures and resource consumed by a specific program. So this picture describes Turing machine model. This is a very simple conceptual model proposed by Turing. You can think that Turing was asking a question: what is the minimist computer? And this is his answer. So basically, within this Turing machine, there is an infinite long tape. You can think the tape as a very, very long array you can use in a computer program. And there's a pointer pointing to a specific part of the array. And there's a computing machine. This whole thing is the computing machine. Let me change the color. So this whole thing is the computing machine. And the computing machine is essentially represented by a state machine. It reads the current value of the tape and update its state correspondingly. For instance, if we were at the state L here and we read them 1, and basically according to the state machine rules here, it will continue to stay at L. But when you reach a 0, it will go to the edge state, right? So basically, what we really need to do is to move around inside this state machine, and by looking at what's there in the tape. And of course, when you update your state, you are also allowed to write back to the infinite length tape, right? So this computing device looks a bit silly, But this entire architecture actually highlights what modern computers should look like. And here, notice that it already has the notion of memory and it has the notion of the CPU. This whole computing machine, device state machine, is more or less resembling the CPU device. Right. Not only that, despite that it is very silly, there's this so-called Turing thesis. This thesis basically says that anything that can be solved efficiently using modern computers can be solved efficiently using Turing machines. But here so let me just write down the conclusions. The statement here. So any problem if can be solved efficiently by modern computers, then it can be solved efficiently by Turing machines. Right. So, but there's a catch here. Like, what do we mean by like solving a problem efficiently? Like, we will be able to see its definition in the next I think in after a few minutes. But this is a mathematical definition over here. So, and there's also another interesting thing, right? So the Turing thesis is actually a very powerful statement. It says that whatever computer you are playing in order to play this particular video, it's no more advanced than this little silly machine. But on the other hand, like, can we implement this silly machine from ground up? Like, it turns out that there's a very interesting book called The Code. It's by the Charles Petzold. So this guy basically teaches you how to implement this kind of silly machines by using the circuits, high school circuit knowledges, right? So long as you know how do you assembly circuits, probably with a little bit extra effort, you will be able to implement a full-fledged Turing machine. You are able to basically build a real computer by your own hand. Anyway, I got over excited about this thing, so let's go back to the business. This is really the key message. Now, given this kind of a strange computation model or whatever computation model that's in your hand, the very first question is that how do we measure computational resource used by a program? So here there are really just the two type of computational resources associated with the Turing machine. One is the running time. Basically, it's really just the number of movements in the state machine, and this is what they say. What it says the number of steps. So you move back and forth. So basically, you count the number of the number of movements. When the number of segment you use that when you travel across this state machine, right? This is the running time. And there's also the notion of the memory. Basically it's really the amount of cells you use in this tab. So in this particular program, it seems that the whole Turing machine only uses that many cells. So basically this is the memory complexity of this program, right? So there's also one statistics people do care about, right? This is really just that the number of states in this state machine. It seems that when you have more states, then it looks that the computer program is consuming more resources, but it seems that for these two metrics we care about here, it doesn't really talk about the number of states. So it turns out that the number of states here, it's roughly corresponds to the length of your code. Sometimes it's really just measured by number of lines, right? So now if you view things in this way, that the whole thing's intuitive. You can have very short program that consumes a lot of resources, or you can have a very very large program that consumes just a little resources. So the number the size or the complexity of the program is not always necessarily proportional to the resources going to consume, right? So this is really the very fundamental question we want to ask about when we talk about a computation model. Oh, by the way, this whole Turing machine thing, it's not really required for our course. You will learn this computation model in further details in CS 243, the theory of computation. Um, but for the purpose of this course, which really the message here is really that there is one or even multiple ways of abstracting out the computation for the actual physical machines. And when we after we abstract out the computation, then we can talk about the time complexity, memory complexity, this kind of things. Right. Of course, for this particular way of modeling computation is maybe a little bit too naive, in the sense that it's both counterintuitive and not fair. It is counterintuitive because nobody is ever trained to write this kind of Turing machine computer programs, right? People are more used to write Python, C, C++, or Java, right? So you really get a extensive you really never get an extensive training on how to write Turing machines, right? And it's also unfair because under this model, even solving simple problems can take excessive amount of resources. For example, if we want to solve the so-called palindrome problem, it's going to take the n square rounding time. So here the palindrome problem is really, a palindrome is really just the English word, so that when you read from left to right, it's the same as when you read from right to left. So here is an example. So the dad is actually a palindrome, right? So the message over here says that if we want to write a program under this Turing machine model, then basically it's going to take us n square rounding time to determine whether a string is a palindrome. But if you write that in C or C++ or Python, then basically this can be determined in linear time. So you can see that although the church Turing thesis says that, well, they are all the computers are more or less the same, more or less resembling what the Turing machine is doing. When you actually compute the time resources we need, we sort of real notice that at least for modern computers, something that only takes linear time is going to take quadratic time for the Turing machines, right? So basically, this is really just a motivation that we need to move away from the Turing machine model. By the way, one final word: what causes this extra overhead? It's deep in Earth. It's really what we call the random access properties. Basically, if you imagine, you go back to program things in a Python way instead of using the Turing machine, then you can always write things like A10, right? Basically, this means that the 10th element of the array. So if you do things in this way, then in Python, basically, it's going to take you constant amount of time to take you to assess the value of the 10th element of this array. But if you do that in the Turing machine, it has to go cell by cell, go there for 10 times, and then identify the 10th element. Right, so basically, the overhead here essentially comes from that the Turing machine doesn't have random access model. Now, let us move to the second model, which is called the word RAM model. This is a more intuitive computation model, and this model is more consistent with our daily experience. In this model, there is a computer program over here. You can think the computer program is just a piece of Python code. And there's also an input array. The input array here stores the information representing the problem you want to solve. For example, if this program's job is to sort an array, then the input to here is the array to be sorted. And there is also an output array. The output array here stores the final output of this program. Again, for the sorting program example, the output array here is supposed to produce the input array in a sorted order. There is also a working memory. This working memory, basically, you can imagine that the program used this portion of memory as the workspace. The random access model, or sometimes people call the word random model, says that if you want to jump to a specific element in this array, then it's going to take you constant amount of the time, right? So this is a lot different from the previous model. When you want to move around, you have to move around from left to right, right? So um so now also notice that there are a little bit of the definitional issues. So usually we assume that the input tab is a read-only one, and the output tab is write-only. And here it's the read and write. So why do we want to come up with this kind of definition? Imagine if you want to be able to solve a problem, basically you are given a very, very giant array, and you want to find what is the max element in this array. And literally what you need to do is really to just look through this array. Just Basically what you want to do is really to look through this array and find out the maximum one, using a very simple looping algorithm. Sorry for that. How can I move that, right? So if you look at this looping algorithm, when it loops from left to right, it only uses very small amount of memory. But on the other hand, the input can be very, very long, right? It can be everyone in the earth. We want to on the earth. We want to find the tallest person in the earth, right? You need to look through 6 billion people here, right? So basically this definition here, like this is read only. The input is read only. The memory is read write. Really try to address this issue, right? This you really wants to decouple the resources used to represent the input from the resources that are really needed to solve the problem. For this particular example, right, the resources that are needed to represent the input could be tremendous, but there's only one temp variable that's needed to really to extract the maximum element in this array, right? So there are some definitional issues here, but of course when you write computer programs to really to efficiently sort array or find the maximum element, you from time to time you ignore this this like what we call the non-reinforceable constraints, right? So just be a bit careful that there's a very subtle difference between the modeling and the real world programming. And okay, there's also a question that why don't we start with just describing this model? This is much more intuitive compared to the Turing model over here. The reason that we don't really like this word RAM model that much is really one major reason is really that we do have a question on whether the memory is infinite or not, right? If the memory is infinite, there's one dilemma we face here. Then how about the index? How large is the index do we need in order to really index all the elements from in the memory? Because the memory is infinite, your index can also be potentially infinite. So then there's a question that how can we even represent a natural number or integer that could be potentially infinite? So there's this kind of loosened end over here, right? On the other hand, if we really forces our memory to only have finite length that's faithfully replicating of what we see in real world, then there's a problem of trying to it becomes problematic to define the asymptotic behavior of an algorithm or problem, right? When you talk about asymptotic behavior, it's really that how as your problem size grows, or as your resources size grows, like in long run, what's the running time change for solving this particular problem, right? So it's really when we talk about asymptotic, it's related to the notion of what happens if things grows to infinite. But on the other hand, you don't allow infinite memory. So now then it becomes very unclear that how do we define the asymptotic behavior. So the very high level message is really that the reason that we don't directly start with the warm model is there are loosened and here and there in the beginning, like at the first glance this model could resemble the programming language you feel most familiar with, but when you look at the details, like it's becomes challenging to tighten up all this loose ends. So after we talk about the computation models, we can talk about the running time of an algorithm. So conceptually, this is how things are related to each other. We talk about the computational models. This roughly maps to the computers in the real world. And when we talk about algorithms, we are talking about how do we run algorithms on top of a specific computational model. Say, for instance, whether we can design an algorithm on top of a word RAM model described above. And conceptually, this is really mapped to the Python code in the real world. Right? So an algorithm corresponds to Python code, and the model corresponds to the computers in the physical world. So now we can talk about the algorithms here under the word model. And there's one type of algorithm we do want to exclude throughout the whole course. This is what we call the brute force. Basically, the idea of this brute force algorithm is really just to exhaust all possible solutions and then find the best one that one can think of. For instance, if we want to travel say from Williamsburg to New York, this is Williamsburg, this is New York, and then we want to be able to find the shortest path or cheapest path, then the brute force algorithm essentially really just search all possible paths traveling from Williamsburg to NYC. It's really just looking for all possible paths, even though some of the paths looks very very strange or very costly. You will nevertheless try to search for that, and after you look for all the paths, you will either find the shortest one or the cheapest one, right? This is usually a very time-consuming search strategy. Usually, when the size of the input is n, then the number of steps that's needed in order to perform this kind of brute force search is usually 2 to the n, right? So this is what we call the exponentially growing, right? What do we mean? Like what do we mean by being able to by having an exponentially growing algorithm? So we can sort of plot the performance of this algorithm. So this is what we are doing. So we want to be able to plot the 2 to the n function, and this really grows very fast. For instance, when n is set to be, say, 100, right? So it's not very large number, right? You just imagine that when your input size only has 100 double, right? It's really just a very small input, right? But when we substitute 100 into 2 to the n, basically this is really larger than the number of atoms in the whole universe. Right. So what does that really mean? The high-level message is really that when you have an exponential running time algorithm, it's going to be very not scalable. Right. So next, we move to understand how we can define the notion of efficient algorithm. We know that when we had an exponential running time algorithm, we call that not scalable. So on the other hand, then basically naturally, when we have a polynomial time algorithm, then we will call that a scalable, right? And sometimes we also call that efficient algorithm, right? So what do we mean by an algorithm runs in polynomial time? Basically, that means that if the input size is n, and the running time can be described as big O of n to the c, where c is a constant, then we call this algorithm is a polynomial time algorithm. C here can be 1, that basically means that this is a linear time algorithm. C can be 2, this can be a quadratic time algorithm. C can even be 100. Now this time it's basically not very scalable, but in theory we still call that an efficient algorithm. So I do want to highlight that the basically what you are seeing here is perhaps the most important message we want to deliver across throughout the whole course. Let me just repeat the most important message. When an algorithm runs in polynomial time, then the algorithm is called efficient. And when the algorithm runs in super polynomial time, or sometimes people call it exponential time, then it's not scalable, so or it's inefficient, right? So 10 years from now, maybe you will have forgotten 90% or 99% of what was taught in this class, but this is the really the bare minimum message we really want you to know after taking this class and after graduation from our college for decades. Okay, so now there's our next question. Why do we really want to use polynomial time as a way to define the efficient algorithm? Let me just erase a bit of what we wrote just now so that I have room for drawing a little bit. So the question is that why do we use polynomial time as our definition of being an efficient algorithm? So the reason is pretty simple, because the polynomial time, the family of polynomials is actually the minimum family that's really closed under under composition. Let me elaborate what do I mean by that. Imagine that we have a team of software engineers. There's an Alice. She wrote a module called A. This module, she can guarantee that this is an efficient module, right? So we don't exactly know the running time of A, but we know that A runs in polynomial time, right? So now Bob comes in. Bob and Alice collaborate in one single project, and Bob needs to rely on Alice component A module in order to finish his own module B. Right? Bob also knows the same piece of information. He knows that module A is going to be efficient module, which runs in polynomial time, but he doesn't really know the exact running time of A. Right? So now he need to rely on A. Let's just assume that he calls A 100 times, right? So let's say just this is really what B is the module Bob is writing, right? For I equal to 1 to 100 and call A, right? This is exactly the very simple procedure, right? So when we view A as a basic operator, we look at this piece of code. We know that this runs in linear time. So let me be more specific. It has a linear number of calls on the running time and then each time we call an A. So basically the total running time would be the size of the loop times the running time for each invocation of A, right? So here we want this kind of closure property, in the sense that if B knows that A is efficient and he just writes a bunch of loops, he doesn't want any surprise. He wants B to be called efficient as well. In other words, if we do the compositions between modules, each of the module is efficient. We don't want the surprising behavior all of a sudden when we put together all the modules, now it's called inefficient, right? So polynomial, the family of polynomials is exactly the smallest family of functions that is closed. This is closed under this kind of what we call the composition operations. And that's the reason that polynomial time algorithm is actually one of the most natural definition of the efficient. So next, this slide is really repeating what I have said just now. Let's just quickly go through these slides. We say that an algorithm is efficient when it has a polynomial running time, and as I mentioned, that there are quite a number of subtle reasons we want to define the polynomial time algorithm to be the efficient algorithm. Just now I mentioned the composition principle. Basically, if we have a set of efficient procedures, and if we do the composition, and at the end the final procedure will also be efficient. Here in the slides provided by Kleinberg and Tadeusz, they they also make another observation that when we define the set of the set of polynomial time algorithm as the efficient algorithm, usually this definition is very robust against the model of computation. Basically, as their origin, using their own words, is insensitive to the model of computation. This really means that regardless whether you are a Turing machine or whether you are a word RAM model, if it's an efficient algorithm under one model of computation, it's very likely to be efficient in another model of computation. Right. So theory-wise, there are, as I mentioned, there are quite a number of subtle reasons we want to define the polynomial time algorithm to be the efficient algorithm, and in practice, we also notice that this sort of definition really works. What do we mean by really works? So this is really just empirical observation. First, we notice that when we manage to come up with a polynomial time algorithm, it's more likely that we come up with an algorithm that's have very small constant. I mentioned just now, even you have an algorithm that's n to the 100, that's also considered as efficient in theory, but in practice, actually it's quite unlikely that we come up with an algorithm with this kind of time complexity. It's more likely we come up with an algorithm with n square, like this kind of very small polynomials with small constants, leading constants, right? And also this is also another empirical observation. So when people start to design an algorithm that moves from 2 to the n to n to the c, somehow we start to be able to break the what we call break through the exponential barrier, then usually that means that we are able to identify some of the very key structures associated with the algorithm problems. And with this kind of key structures observations, usually we can quickly reduce to this kind of theoretical algorithm to a very practically relevant one, right? So in other words, it's really that usually when people start to move from exponential time to polynomial time, then new algorithm is discovered. Right? So again, there's always a question that whether this kind of definition it's really sensible in every single scenario. Like one of the favorite question is that if we do have two algorithms, one is polynomial time algorithm with a coefficient of 1 to n to the 120, and the other one would be an exponential time algorithm, but the coefficient is very, very small, right? So it's 0.02 times log n, like the exponent here grows very, very slowly. So in practice, which of these two algorithms runs faster, right? I think for all practical problem and problem instances, it's very likely that the exponential algorithm is running faster. But in theory, we still call the first one to be the efficient one and the second one to be inefficient one. There again, like when we build a model of computation, we talk about the theoretical results. There's always sort of a gap between theory and practice, and this is an instance that there's some sort of discrepancies. When theoretically an algorithm is better, it's not necessarily true that in practice the algorithm is better. So now, our definitional game is not ended yet. We start with a definition on the model of computation. Then we want to define the notion of efficient algorithm. Basically, we say that an algorithm is efficient when it runs in polynomial time. Now, there's this extra question, and what is the running time of an algorithm? This really boils down to the very, very basic question. So for instance, if you design an algorithm, sometimes it runs fast, sometimes it runs slow. Do we measure the fast runs or slow runs? And here, usually, what we really care about, it's called the worst case. We want to understand the algorithm's behavior in the worst case. That is, if I consider all possible input, I want to understand which specific input has the slowest running time. And usually we use that slowest running time to characterize the performance of an algorithm. Right? So So there are two reasons we want to do the worst case running time analysis. The first reason is that generally the worst case analysis are able to capture the characteristics of the algorithm pretty well in practice. So this is another empirical observation. And second, there's also a very practical reason is that if you don't do the worst case analysis, actually the math and analysis is going to be much more difficult. So in other words, in a lot of situations, the worst case analysis is the only analysis we are able to do, right? We also want to mention a catch here though. There are a lot of algorithm that has the worst case exponential running time, but that runs very well in practice. And actually, these are the three examples. The first example is called the simplex algorithm. It's an algorithm that solves linear programs. In case you have learned the linear programs in the math department, then you sort of knows what I'm talking about. And the second example is the grep command in Linux. I think perhaps it surprises some of you that this algorithm actually has exponential running time in the worst case. The third one would be an example in the machine learning. It's called the k-means clustering algorithm. Basically, the high-level idea is that you are given a set of points and then you want to cluster the points into different groups so that each of the so that points within each of the group represents things in a similar class. For instance, you may cluster the height of all human beings into two groups. Then basically, roughly you will see a male group and a female group, right? Because of their height difference. Right. So I also want to mention that there could be other ways of doing the running time analysis, right? Let's just briefly mention two possible ways. The first way would be the probabilistic analysis. This basically means that there are some algorithms when it runs, it tosses coins. And that really just means that even for the same specific input, sometimes the algorithm runs fast because it tosses one coin, because the outcome of one coin is behaves in one way, and sometimes it runs slower because we toss a different set of coins. And under these situations, we are interested in understanding whether we can talk about the expected amount of time needed to execute an algorithm. So basically, we care about expectation over the coin tosses, the running time of the algorithm. So the running time here is a random variable. That's a function of the coin tosses, right? So this is what we do the probabilistic analysis. The second category of analysis we sometimes care about is what we call the amortized analysis. You can imagine that you execute the same algorithm 3 times. For instance, you want to sort 3 columns in Excel sheets, and if you want to apply this algorithm multiple times, imagine the first time the running time is 10 seconds, the second time it's 1 second, the third time is 2 seconds. And then our question is that how can we characterize the running time? In the worst case analysis, we do care about the what happened in the worst possible case, right? So when we talk about worst case, then we say the algorithm runs in 10 seconds. But sometimes it also makes sense to really just ask that to characterize the running time by the average running time over multiple runs. So the amortized analysis really just captures this intuition that when we take the average, this number is sometimes meaningful.